So, welcome to the final lecture of this course, Strong Field Laser Physics and Attosecond Laser Physics. What we want to do today is to look at high harmonic generation again, but this time on the macroscopic effect. Well, actually, it will turn out that we also need to deal with the microscopic effects. And as you might expect, these are the particularly interesting ones. So we will look at phase matching of high harmonics. Well, let's start with a general description of the problem. So what I have here already is the focus of a laser beam, say of the laser beam that generates the high harmonics, right? And then you could assume, and this is actually usually the case, that our target gas, so the gas that produces the high harmonics, that the extension of that gas is larger than the focus. At least it's not confined to a small fraction of the focus regularly. So this means that we generate, at least in principle, throughout this focus, we generate harmonics, right? So we generate harmonics here, we generate a little bit of harmonics here, probably more there in the center of the focus where the intensity is highest, and so on and so forth. And the question is, of course, whether all these, let's say, elementary emitters or elementary rays that are generated here, whether they arrive in phase in the far field, right? So this is pretty much the same thing, so the same kind of problems that we would have in nonlinear optics there. It would be a crystal, and we would ask whether all the emission in the different regions of the crystal, whether they interfere constructively. This is phase matching, right? Here this thing is a little bit, well, it's a little bit special. Okay, so what we do in order to address that would be that we say that we define here, well, a small volume. I call it a voxel, yeah? A volume pixel, so a voxel. Okay, so let's write down a few remarks, and we consider, yeah, so the emission of this voxel for a certain harmonic, say the Q's harmonic. Let's write that down. We consider a specific harmonic say the Q's harmonic and now in each voxel, yeah, some Q's harmonic radiation will be generated. So in each voxel, some Q's harmonic radiation, and I would call it d psi q. Yeah, so Q for the Q's harmonic, and similar to diffraction theory, yeah, so I would write here R prime. Yeah, so the voxel has infinitesimal volume, and therefore I write an infinitesimal a wave here. So this will be generated, Yeah, and the question now is whether they interfere, whether all the d psi q, whether all of them interfere. Yeah, so the question is, well, they interfere, but the question is whether they interfere constructively. So the question is whether all d psi q interfere constructively for all R prime. Yeah, so for all positions in the focus. Okay, well, there is fortunately one thing that we know for sure. We know that that this elementary wave, well, is a wave, and therefore its phase develops as the phase of a wave develops. Yeah. So we know the phase development of dq, deep psi q, as it is a wave. So what we know is that this phase phi of this high harmonic q at some point, at some distant point, say a screen or something like that, right? That is given by omega, by q times omega times t, right? So omega, this is the fundamental here. Yeah, so this here is the fundamental. Of the laser, right? And now we have to write down also the other part. So I split off the refractive index at the Q's harmonic, so the refractive index in the XUV. I call this NQ. And then we have the wave vector. This is just 2 pi over lambda q. And then we would have r minus r prime, right? So something like this. Yeah, so this here would be the point of observation. This here would be the position of the voxel. This here would be the refractive index. Yeah, and this here is 2 pi over lambda q, so which means lambda of the laser divided by q, right? Okay, so that's equation 1. To make things simple, we confine ourselves to a position on the screen which is on the optical axis. Yeah, so somewhere downstream here, so if the laser would come from this direction, we would look, well, a meter behind or something like that, right? And just see what we would get. Yeah, and on this screen, we would say that the phase for each of these, so for each of these elementary waves should be the same. Yeah? Then we have constructive interference. Yeah? Okay, let's write that down. So now we could look at a point R on the screen. Yeah, so for simplicity, a point on the optical axis, yeah, so in the center of the screen. For simplicity, a point on the optical axis. Generalization to any other point is trivial. We'll briefly come to that. Yeah, so for this point, all deep psi q of should arrive So I could write here of R prime, should arrive with the same phase. This is what perfect phase matching would demand. Well, and any deviation would be, of course, a mismatch. And then from that point, we could follow back each ray, right? So each ray back to where the voxel is, and then say, well, which is the phase with which I need to generate actually the harmonic such that after this propagation they arrive all with the same phase, right? Well, just to motivate this a little bit more, so what you have to consider is that we have, well, that we might have different gas density in this volume. In particular, we will definitely also have free electrons that produce a refractive index. So we have an inhomogeneous medium here, right? And therefore, the different rays that we propagate back, yeah, so for a voxel, say here, and another voxel there and there, they pick up different phases. Now, and the question is, to put it the other way around, at which phase do I need to produce the harmonic at the different places such that at a distant point on the screen, say, they arrive with the same phase. Yeah? Okay. Yeah, so then we can follow all rays back to the voxel where they were created. And determine the phase accumulated on this path. And therefore, this gives us the information with which phase the harmonic, the qth harmonic in this case, should be created such that all rays arrive on the screen with the same phase. The same phase. Yeah? And if we want to, say this in mathematical form, then we would say that that this phase with which they should be created, we call it the polarization phase. Yeah, so it's a polarization that causes the emission of the harmonic. So that the difference between this accumulated phase on the during the propagation, that this shouldn't vary with position. Yeah? Okay, so this is the phase with which the qth harmonic, well, yeah, so I wrote that actually already. So this phase, yeah, so let's write it like this. So this phase is called Phi Polarization. So, and phase matching demands simply that the derivative, and if we look just on the optical axis, then it's just the derivative with respect to z of phi polarization minus phi high harmonic generation. Yeah, for the Q's harmonic I could add, but sometimes I just leave that out. Yeah, so this is the condition. Yeah? And now we can generalize this to off-axis positions. So usually, actually, so most of the time we just consider points that are close to the axis. But of course, it can be generalized quite trivially. So for off-axis positions, for off-axis directions, I should say, directions, we expect, of course, that that the phases run out of phase more quickly. So if you, that's the reason why a beam propagates on straight lines, yeah, because the molecules it excites there, their radiation is out of phase for all directions different than the beam direction. Yeah, so quite obviously. So for off-axis directions, we expect for high harmonics, it's not always fulfilled, I have to say, but we may come to that later. We expect that the rays from different voxels run out of phase more quickly. Yeah, same as in usual optics, even linear optics. Yeah, so in general, the phase matching conditions condition would be like this. Yeah, it's the gradient. The phase mismatch is the gradient of this difference of these phases, of these two phases. Yeah, and this delta K is referred to as the phase mismatch. As phase mismatch. Yeah, just the same things, yeah, in the same spirit as in nonlinear optics. And we may also introduce the coherence lengths. Yeah, so it's the coherence lengths of nonlinear optics. You know that in regular optics, there's also a quantity called coherence lengths, which is something completely different. Yeah, so coherence lengths. Yeah, so when we get out of phase, then the elementary waves start to interfere destructively. Yeah, so they lose their, well, in some sense, their coherence. This is why it's called coherence lengths. I don't like this name very much, but it's called like that, so what can I do? Okay, so, well, this means that with this kind of analysis, we are almost pretty much done, in principle. Yeah? So if we assume that we know the refractive index of the medium, yeah, then actually pretty much everything is said. The only thing that remains to be known is the polarization phase. Yeah? Okay, yeah, so assuming that we know the refractive index of the medium, yeah, so of the gas, the only problem, well, and, this is of course that this only problem sounds harmless, but of course the only problem is usually the thing that makes or causes the work. So the only problem is to compute the polarization phase. Yeah? And once this polarization phase is known, the macroscopic field can easily, well, perhaps it's not easy, but it's at least straightforward. Yeah? So can be computed in a straightforward way. Yeah, we just use the superposition principle. Yeah, we add them according to the amplitude and to their phase. Okay, so now we need to look at the phase of the excitation. Yeah? So the problem is that we have a focused beam, right? And if we look at a focused beam, then it's different from a plane wave. This is the essential point. A focused beam is different from a plane wave, and we call this the geometric phase. Yeah? So this is 8.2, chapter 8.2, the geometric phase. No, the polarization phase is the phase of the polarization. Yeah, so the laser excites the polarization, yeah, and excites the atoms, right? And in this way, some polarization is created, right? But of course, if you change the phase of the laser, also the phase of the polarization will change, right? So definitely the phase of the laser and thus the geometric phase will have a major impact. Yeah, so we need to add this to the, so this is part of the phase of the polarization. Okay, the geometric phase. Yeah, so first remark goes exactly to your question. Yeah, so the polarization phase will definitely contain the phase of the exciting wave. Yeah? The phase of the exciting wave, which is of course the laser, the fundamental of the exciting wave, which means the phase of the fundamental. Yeah? And the fundamental is a focused beam. Yeah? And its phase is, of course, the phase of a plane wave plus some geometric phase term. Yeah, so its phase is the phase of a plane wave plus some geometric phase, which is well known. At least people believe that it's well known. Yeah. And this phase I call phi geometric. And it depends, of course, on z prime and r prime. Right? So r prime is now the radial coordinate, and z is the coordinate on the axis. Okay, yeah, so this means that the excitation polarization, this would be written as omega times t. Yeah, so omega is the frequency of the fundamental. Yeah, so frequency of fundamental as before. And then we have, of course, n of omega, yeah, so the refractive index at typically visible or infrared wavelengths, times now the k vector, yeah, so given as 2 pi over lambda, say for titanium sapphire laser 2 pi over 800 nanometers, and then we have here r prime minus this geometrical first phase term. Yeah, so something like that. In the following, I will drop these primes because I get tired of writing these primes all the time. Okay, as I said, for at least for monochromatic Gaussian beams, yeah, you would immediately say, well, when is a beam Gaussian? Perfectly, yeah, and in particular, you would say, I need short pulses, they are never monochromatic. But nevertheless, let's do this assumption. At least as long as the pulse is not too short, it's actually a reasonable approximation. For a monochromatic Gaussian beam, the geometrical phase is phi geometrical. We have the arcus tangens of z over z0, which is the confocal parameter. And yeah, so you see an arc tangent-like behavior of the phase. Yeah, so it changes by, the phase changes as we go through the focus by 180 degrees. Right, so it's actually also something that's relevant for regular nonlinear optics. But the phase fronts, they are also curved. Right, so we have 1 plus z0 over z squared. Yeah, so it looks like that. Yeah? Equation 4. Yeah? And the first term, this is the well-known GUI phase. Yeah, so where the first term is the well-known GUI phase. Well, a little anecdote here at this point. So here we first have Louis Georges Gouy, a French scientist, yeah, and this is why he's pronounced that way. Anthony Siegmann, a famous laser physicist who wrote a famous book on lasers. Yeah, so here you see an old copy here. He introduced an alternative writing of GUI. Yeah, so with GUOY. Yeah, and well, and everybody who read this book, and there were many physicists reading this book, followed his example and also wrote him the wrong way. So he actually came once when I was still a PhD student. He came to Garching and to visit the Max Planck Institute of Quantum Optics. And I had to explain to him my poster. He was a very friendly man. Right? And he said, well, I'm delighted that you read my book. And I said, what? And he said, yeah, you write it the same way that I wrote it, but it's wrong. Yeah, so this is how I learned that you should write it this way. Yeah? I'm not sure whether a later edition of this book, whether it was corrected or not. Okay. A little anecdote. Yeah, so we can look at the phase distribution. Yeah, so this is, here you see the contour lines here, they are lines of equal phase. Right? Looks quite funny, the phase distribution in a Gaussian phase. But if you just take the cut through this here, then you get this curve here. Yeah? So this holds for monochromatic beams. If we have a few cycle laser beam, then things get complicated, right? Because each of these colors, and if it's a few cycle pulse, then it can span an entire optical octave. So basically span the entire visible range, right? And each of these frequencies is focused if you use a focusing element, and you need to use one. Each of them is focused in a different way, right? So the blue colors, they will have a smaller focus than the red colors. And now, of course, it depends on how the different colors are distributed in the laser beam, right? So when you generate, you all the time you deal with a very complex situation. So typically, you may use a fiber compressor, right? Then at the exit of the fiber, the diameter of all colors is probably pretty much the same, right? And you would focus them, then all of them have a different divergence. Yeah, so really a lot of fun. Yeah, complicated situation. Yeah, so and once we investigated this together with the group of Peter Hommelhoff in Erlangen, and we took a near-field probe here to measure the GOI phase in a certain, for a certain few cycle laser beam, and you see that it doesn't behave. It doesn't behave like a Gauss, so this here would be the Arcus tangents. This the dash curve would be the GOI phase, right? And it deviates significantly, right? Okay. Well. This is still in the vacuum. Yeah. So this is. We focus this in actually a ultra-high vacuum apparatus. So it has nothing to do with medium.
Why is it so far away from the
Yeah, well, because so the question is why it is so far away from the GOI phase. Because the bandwidth is so broad. Yeah, so we used 4 or 5 femtosecond laser pulses. And this means that the blue that we had almost an entire optical octave, right? So the wavelengths at one end is half the wavelengths at the other end. And now, if you look at you know the formulas for the beamed waste. It depends on the wavelengths, right? So there are strong effects of that. Well, now it depends on how, so you could still say that this is similar to this dashed curve. right? So actually, the situation is even more complex. It depends on which distribution of divergences and beam diameters and so on you have in your beam. Yeah? So the Goy phase or this focal phase can also have this behavior. Then it's really different. Okay, but to produce such a distribution wouldn't be so easy. Okay, well, yeah, so one important point to make here is that the fundamental wave is not only inhomogeneous with respect to the phase, but of course also with respect to the intensity, right? And this causes, and we know that the processes inside the atoms that go on when high harmonics are produced, that they do depend on the intensity, right? A specific harmonic, so if you look at a specific harmonic, say if you look at the 25th harmonic, right, that is produced at different intensities, then the trajectories that led to their production are different. Yeah? Okay, so let's write that down. Yeah? So the fundamental wave is also inhomogeneous in terms of intensity. That's a trivial remark. But the consequence is a given harmonic produced at different intensity will originate from different trajectories. Yeah? So in particular, different T0 and T1, so different times at which these trajectories were born and at which they recombine. Yeah? So, and this gives rise to another phase factor or to another phase term, not factor, phase term, namely the polarization due to the emission time, right? This means that the polarization phase, this is the sum of the excitation plus the polarization for the emission. And that's often called the atomic phase. And the atomic phase is kind of the most interesting ones if we speak about strong field laser physics. So everything else is, from the viewpoint of strong field laser physics, trivial, more or less, but the atomic phase is not. Yeah? One has to say that the atomic phase is often not the dominating phase. It's not the dominating contribution to phase match to phase matching, but I would claim it's the most interesting one. Okay, at this point, I would say we do an interim review, yeah, so kind of an interim summary, and just list which factors contribute to phase matching. And then we'll have a small break and continue afterwards. So an interim summary. So there are 4 contributions. There are 4 contributions to phase matching. Of high harmonics. Yeah, so the first one would be the refractive index of gases, of the gas that we are using. Then the refractive index of the free electrons. Then the geometric phase, the Gauss phase in the simplest case, and the atomic phase. Yeah. And as I said, the first 3 items, they are trivial in the sense that they are textbook knowledge and can be looked up in the internet. Right? So the refractive index, for example, here I have a resource for you. So these are the so-called Henke tables. So if you just Google Henke tables, then you would end up at this web page, right? A fairly old-style web page, but nevertheless very informative, extremely informative. And here you find the link index of refraction for a compound material. Now it also works for a uniform material, right? And if you click on that, then you get a mask like this. And here I entered already something. Yeah, so argon at a density of 1.6 gram per cubic centimeter. That's of course a lot, right? But actually, I tried to enter 1.6 10 to the minus 6 gram per cubic centimeter and doesn't like that. But of course, I can divide through 10 to the 6 or the results, right? And then you can type in the range in which you want to know it, and can request a plot or a text file, right? And if we look at the plot, then you would get something like this. Yeah? So we get the delta, which is the refractive index, or the difference of the refractive index with respect to 1. So 1 minus delta is the index of refraction, right? So the real part, right? So this is this blue curve here, and beta is proportional, or so it describes the absorption. Yeah? And we'll come to the absorption in due course of this lecture. Okay. Yeah, also we write this to our summary. Yeah, so the first 3 items are trivial. Yeah, this is not a friendly word, but so refractive index, we would go to the Henke tables. Then the free electrons, we would take a textbook, and we would find that the refractive index of the free electrons, this is of course basically given by the plasma frequency or in other words, by the density of free electrons. Yeah, so the refractive index is a function of omega, and the formula for the plasma frequency is 4 pi a square density of the electrons, yeah, divided by the mass of the electrons, omega squared still. Yeah? So that here is density of electrons. Of free electrons. Geometric phase, at least for an approximation, the Gouy phase, I have to pay attention to the Gouy phase, I should say, yeah, so he's a Frenchman, Gouy phase. And the atomic phase, well, see below. See later. Right? And we have to balance these 4 contributions. I have a slide for that shows this balance. I've stolen this figure from the dissertation of Robert Klaas, who wrote an extremely beautiful work on that. So he calls it the intrinsic phase, what I call the atomic phase. Then this is the refractive index of the atoms. So in general, this gives a delta K smaller than 1. And then we have the Gouy phase and the phase due to the free electrons, which give a positive contribution, right? And if you balance it in the right way, then you can achieve delta K equal to 0, at least in some subvolume of the focal volume. Yeah? And we'll analyze this in the next lecture in a little bit more detail. So see you in 5 minutes or 3 minutes or whatever. Thank you.